Missing gas capacity, an adverse effect of subsidized renewable energies. Matthias Vriens and I wrote a study entitled "Do Intermittent Renewable Energies Threaten the Electricity Supply Security?" The study was published in Energy Economics in 2020, so dating a few years back already. However, we argue that today the study is more relevant than ever. Why is that? There has been an ongoing controversial debate in Germany. We find headlines about issues of electricity supply security and missing gas power plants. There's even a government proposal entitled Power Plant Strategy, which argues to build at least 20 gigawatts of new gas capacity in Germany. What is this all about? Let's break the debate down in very simple terms. On the one hand, there are people arguing that we need additional gas capacity to balance the supply intermittency of renewable energy, which is driven by the weather and which does not follow electricity demand. Moreover, people argue that in the future, those gas plants should be fueled by hydrogen to ensure CO2 neutrality of the system. On the other hand, people argue that gas plants will keep the fossil industry alive and hinder, therefore, the energy transition. It is further argued that significant amounts of hydrogen as a green fuel are an illusion. It is not clear where this hydrogen should come from, and therefore Germany's climate goals are at risk. So that is a huge controversy. What is our study about? We are testing how renewable energy affects investment in gas-fired power plants. The study was conducted during 2017 and 2018 and then eventually published in 2020 in the journal Energy Economics. We are applying an econometric model using data from 14 European economies during 2004 through 2016. That was a period which was characterized by very low carbon prices within the EU emission trading system. Carbon prices of, on average, significantly lower than 10 euros per ton of CO2. However, this period was at the same time characterized by high financial support payments for renewable energies. So why do we do our study? On the one hand, we are addressing a supply security issue. Gas-fired power plants, which are flexible in their electricity output, are an ideal backup for the volatility of renewable electricity supply. On the other hand, there are environmental benefits of gas-fired power plants. Gas plants have significantly lower CO2 emissions and significantly lower toxic air pollution than lignite and hard coal. Let's look at a stylized graph of supply and demand showing the workings of subsidized renewable energies in a system that is characterized by no or a very low CO2 price. We have different electricity supply technologies in a price quantity diagram, and for given demand we get an electricity price. The electricity spot price is characterized by the marginal technology, which is here gas. Now countries are subsidizing renewable energies via financial support, and therefore renewable energies are deployed and pushed into the system. They shift the remainder supply curve to the right, and the electricity price falls for given demand. So firstly, we observe a falling electricity spot price, which is the so-called merit order effect of renewable energies. Secondly, we observe that gas is pushed out first, hard coal becomes marginal, and lignite can remain in the system. This is, however, an undesirable outcome, because we want to have gas rather in the system and lignite and hard coal being pushed out first. Let me come to the empirical model. Our hypothesis is that more renewable energies reduce investment in gas-fired generation capacity. And we test this hypothesis in a panel econometric dynamic investment model. Since a dynamic investment model includes a lagged dependent variable, so lagged investment, there may be potential endogeneity bias from this system, and besides OLS fixed effects, we are therefore also estimating this model via instrumental variables estimators such as LSDVC and GMM. Given that this is advanced econometrics, I'm gonna skip the discussion around those estimators for now. Our model is then essentially gas investment in country I in year T as a function of renewable electricity together with control variables, a time trend, and country fixed effects. Beta is then the coefficient estimate of interest, which measures the effect on gas investment when renewable energies increase by 1 percentage point. According to our hypothesis, beta should then be negative and statistically significant, meaning a negative effect on gas investment. Identification comes from our exogeneity assumption. We assume that renewable energies, which are driven by the weather and other control variables, are largely exogenous. And during our sample period, this seems a valid assumption. If our variables are indeed exogenous, beta can be interpreted as a causal effect. Let's now look at some descriptive observations. On the left-hand side, we see the share of renewable energies, which is across our sample countries increasing over time. This increase in renewable energies is financed via state support payments. And on the right-hand side, we see the share of gas-fired generation capacity, which is rather stable on average. So from pure descriptive observation, we do not observe a clear relationship between renewable energies and gas investment. Gas investment appears unaffected by renewable energies, and therefore we are curious now about the econometric results that control for additional influential factors. Let's come to the main econometric results, and for now we only look at our primary estimates from the LSDVC model. We indeed observe that the effect of renewables on gas investment is negative and statistically significant. The coefficient estimate of negative 0.4663 implies that one additional percentage point increase in renewable energies lowers gas investment by 0.47 percentage points. And this is in line with our main hypothesis. Let's now interpret this coefficient estimate. Most countries in Europe, such as Germany, have ambitious climate goals and will further deploy renewable energies. During the period 2012 to 2016, renewable energies rose by 4.25 percentage points in our sample. And that implies that the gas investment rate would change by minus 1.98 percentage points. We can then evaluate this changing investment rate at the final year 2016 gas investment rate of minus 2.47%. So therefore our model predicts an investment rate for gas capacity of minus 4.45% per year. There is an exponential behavior behind this investment rate, and therefore our model predicts that gas capacity would fall by 20% within only 5 years, taken as a ceteris paribus effect, so holding all the other influential factors constant in our model. And this is not good, given that we would rather have gas in the system than lignite and hard coal. Our estimates also help explain today's shortage of gas capacity in Germany and some other European countries. Let me also briefly come to estimates on baseload and coal generation capacity. Here, across different models, we find that renewable energies do not impact baseload or coal investment. We see no statistically significant effects, and therefore, with no effect detectable, that basically supports our main theory that renewables push out first gas, whereas coal or other baseload technologies can remain in the system. What are some problems associated with our findings? We find that there is a significant underinvestment effect in gas-fired generation capacity and that this is problematic. Firstly, there is a supply security issue. Renewable energies which are driven by the weather need flexible backup capacity. Gas plants are therefore ideal because they flexibly ramp and cycle their electricity production according to variations in renewables or variations in electricity demand. Secondly, there is an environmental issue coming with our effect. Lignite and coal can remain in the market while gas dies. Lignite has tremendous CO2 emissions and tremendous toxic air pollution impacts. Gas is significantly cleaner as shown in the table below. And therefore we have an environmental problem. Coal remains while gas fades. So what would be a better policy design? I argue that a market-based carbon pricing approach would be the better policy. Rather than direct financial support for renewables, we should use a market-based climate policy with a sufficiently high CO2 price. Let's now look at our different supply technologies again in a price quantity diagram, but now we have a significantly higher CO2 price in place. The CO2 price is associated with the emission factors of the different supply technologies. Nuclear has no CO2 impact and therefore the CO2 price does not change the marginal costs of nuclear plants. However, lignite and hard coal with their very high CO2 emission factors now have to pay a significantly high CO2 price and therefore their marginal costs are significantly more impacted than gas's marginal costs. That is why gas swaps places with lignite and hard coal. Gas pushes in first and only then hard coal and then lignite. For given electricity demand, now we have a higher electricity spot price. This time lignite is the marginal technology. When now renewable energies push into the system and shift the remainder supply curve to the right, we only see a significantly lower falling electricity spot price, but now gas remains in the system and hard coal and lignite are being pushed out for their higher marginal costs from a higher CO2 price. That would be a smart policy design which essentially keeps gas as a flexible backup technology in the market, pushes out the dirty emission technologies, and at the same time deploys renewable energies. If you're interested in renewable energy, energy systems, and policy and markets, please hit the like button and subscribe my channel. That really helps me develop new videos. Let me come to the conclusion. This study empirically uncovers an unintended effect of a non-market-based policy. During times of low CO2 prices, subsidies for renewable energies push out gas capacity while coal capacity remains in the system. Underinvestment in gas capacity creates undesirable outcomes. Firstly, there is supply security at risk. Missing gas as a flexible backup for renewables means that other technologies which are not designed for ramping have to balance renewables, and that is problematic. On the other hand, highly pollutive coal can live while cleaner gas dies. This is again not what we want from an environmental perspective. So this all helps explain today's shortage of gas capacity in Germany. A high CO2 price would induce a fuel switch between gas and coal. Then renewables would push coal out first and gas could remain in the system. That would be a smart policy which has not been followed by our policymakers in Europe during that time. Currently, despite a higher CO2 price of around 75 euros per ton of CO2, a high gas price due to the tensions with Russia prevents a fuel switch between gas and coal, and therefore the CO2 price would need to be even higher than 75 euros.